Pardon me. All right. Well, let's talk more about diagonalization. So again, the idea behind doing diagonalization is that we want to find, hopefully, we can't always do this. We'll talk about what happens if we can't do this. But the goal is to figure out a diagonal matrix and some other invertible matrix P, so that I can write A as that PDP inverse. So again, the reason why we would like to do this, again, is some applications require us to take higher and higher powers of the matrix. If we can do higher and higher powers of the matrix, we can do higher and higher powers of this side instead. And we notice that, we'll say like we had A squared over here, notice that we can just move kind of the squared to the inside, right? And if you do A cubed, it would be the same kind of thing. The cube would go to the inside matrix there. And it's a lot easier to do a power of a diagonal matrix, because all I do is just do the powers down the diagonal, rather than doing the powers of the matrix, which would be, rows times columns over and over again. The computational expense is a lot less. Okay? So that's the whole reason why we do that. Okay. So we talked a little bit about yesterday about when we can do that. So we said, or on Wednesday, I mean. So we said this is more of the situation that we were looking for. If I have an AP equals a PD, if that's what I want to set up, then I notice that the left-hand side, when we do the product, I can think of just taking the A times each of those individual columns. On the right-hand side, if I put the diagonal matrix on the right, then that's like multiplying each of the columns by those diagonal entries. If I'm going to have equality, then I see that AP1 needs to be lambda P1, lambda 1 P1. AP2 has to be lambda 2 P2, so on down the line. So what I really want that matrix P to be made up of are eigenvectors, and then the diagonal matrix will be our eigenvalues. Okay? Now, in order, of course, to be able to invert the P and move it to the other side, I need to make sure that we can find n linearly independent eigenvectors for the matrix. Okay? And you can't always do that. So that'll be we'll talk, like I said, we'll talk a little bit about that later. All right, so let's just go ahead and do an example here where we're going to diagonalize a matrix. So we'll do this with our calculator, so we don't have to go through all the computations by hand. Okay, so we've got this matrix here, A. Let me switch over. So I've got 8, -4, 1, 9, -9, -1, -18, 12, -1. If I could type, that would be helpful. Yeah, I know, I didn't hit the 1. There we go. All right, looks like I've got things entered in there correctly. So remember that, and this is probably already still saved in my calculator here. Remember that we can graph the characteristic polynomial by just doing determinant of whatever matrix we're trying to find the eigenvalues for minus x times the identity matrix that's the appropriate size. Now in this case, we have a 3 by 3 matrix, so I need to scroll over and change that 4 to a 3. And graph it. We've got a 3 by 3 matrix. So our characteristic polynomial would have degree 3. So I'm going to have at most 3 distinct roots of my characteristic polynomial when I'm done. In this case, I really do have 3 distinct roots. You could use if it doesn't look like it's crossing at the axis points here, I could use my calculate feature and find the zeros of that function. Maybe like if you had something like -3/2, maybe you want to verify that really is -3/2 by using that. But in this case, it looks like we've got -3, -1, and 2 as our eigenvalues, right? So I flip back over just real quick. I'm going to come back to the calculator as well, but we do the determinant of A minus lambda I equals 0. That's how we set it up, right? If you were to do this by hand, you would have your matrix set up like, oops, put my minus lambda there. Set up that way, and then you'd have to use your determinant properties, right? Do an expansion by minors or a row reduction. That'd be a lot of by hand work, right? So I wouldn't make you do something this ugly by hand. It's not all that ugly, but it still would be a lot of work to try to do all the multiple. Notice we don't have a lot of zeros here, right? So we don't get a lot of those cancellation things that we like for determinants. So you have to do a lot of multiplying out your polynomial, and then trying to refactor it. Be a big pain, right? So I'm not going to make you do that by hand. I wouldn't expect you to use your calculator on something like this. Okay. All right. So again, when we solved this, we said we saw -3, -1, and 2 look like they were the roots, right? Okay. So in this case, we've got 3 distinct eigenvalues. We're not going to prove it, but it turns out that when you have distinct eigenvalues, if you've got associated eigenvectors, so if I take an associated eigenvector with -1 and -3 and 2, those 3 vectors themselves will be linearly independent. If you change eigenvalues, the eigenvectors change and they are independent of the others. You can actually prove that. It's not too bad of a proof. Just for time purposes, we're not going to prove it. Right? So since we've got a 3x3 matrix, and since we have distinct eigenvalues, we can diagonalize this matrix. We can find 3 linearly independent eigenvectors to create our matrix P. Okay? If you've got repeated roots, that's when you may or may not be able to diagonalize. And again, we'll see an example of that here later. All right, so let's flip back over to the calculator. Let's figure out what these eigenvectors are. So remember again, we'll use our reduced row echelon form command of the matrix minus the identity times, and then we'll plug in the eigenvalue here, right? We've got 3 different ones to plug in. So the first one we had was -3. And if we want to convert that to a fraction, I can do that with the under math to a fraction key. And we can see that we've got 1, 0, 1/3, 0, 1, 2/3, 0, 0, 0 is our reduced row echelon form. All right, so let me flip. Are we okay with this command, by the way, typing it in this way? Is that okay? Good. All right. So back over here, the reduced row echelon form for lambda equals -3, our reduced row echelon form is 1, 0, 1/3, 0, 1, 2/3, 0, 0, 0. Again, remember, when you do this reduced row echelon form, you always have to see at least 1 row of zeros. If you row reduce and you get the identity matrix, you don't have an eigenvalue. Okay? The eigenvalue needs to create non-trivial solutions to the homogeneous system. If you get the identity matrix, you don't get non-trivial solutions. Okay? So if you plug an eigenvalue in, or what you think is an eigenvalue, and you get the identity matrix, you don't have an eigenvalue. Okay? One of the reasons I'm emphasizing that is an error I see quite a bit. So make sure that you get non-trivial solutions. All right. So now, if I'm looking for a basis for the eigenspace here, what would we use for a basis for our eigenspace? We should be able to read this off now. Where is your free variable? Yeah, it's column 3, right? So for our eigenspace, our basis, we do have a 1 down here, right? And then, so if we do x1 and x2, what would they be? Good, -1/3 and -2/3, right? When we move it to the other side, we just subtract them over. If you don't like the fractions, what could you use instead? Yeah, I can multiply everything by 3, right? Any scalar multiple also works. So if you don't like the fractions, multiply everything by 3. Use -1, -2, 3. as your vector. Which I'll probably use that anyway for the matrix P. Because if you're going to do computations, you might want to get rid of the fractions. That okay? We do the exact same thing for the other two. We flip back over. Oops, flip back over. Actually hit the button. So I'll do second entry. If I hit it again, I can grab it. Or you might want to scroll up and go grab it. Whichever way you want to go grab the previous entry. I don't really care how you do it. Change the -3 to a -1. I see 1, 0, 1/3, 0, 1/2, and 0, 0, 0 for our reduced row echelon form. Write that down while you're looking at that. So it says 1, 0, 1/3, 0, 1/2, 0, 0, 0. I'll flip back over here. And now again, free variable is in that third column. You would subtract your third and subtract your half. And you get -1/3, -1/2. 1 works as a basis. Or again, if you wanted to clear your fractions, multiply by 6 and get -2, -3, 6. Your choice. You can leave it as fractions or you can clear them. Or you can make new fractions. Doesn't matter. It's okay? All right, I'm not going to flip back to the calculator since we seem to be comfortable with getting it off the calculator. If I row reduce that by plugging in 2 and actually delete the last parenthesis off, for lambda equal to 2, our reduced row echelon form looks like 1, 0, 1/2, 0, 1, 1/2, 0, 0, 0. And so your basis for your eigenspace here will be -1/2, -1/2, 1. So far, so good? This is not new. We've done this stuff, right? The new part's literally just creating our diagonalization. So our matrix A, again, we want to write it as P, D, P inverse, right? D is diagonal, P is invertible. Again, we have to have 3 linearly independent eigenvectors to make this invertible in this case. But we do, since I've got 3 distinct eigenvalues, or 3 distinct eigenvalues will give me those 3 linearly independent eigenvectors. So here's how you create your matrices. Order doesn't matter as long as you're consistent. So what I mean by that is I can use -3, -1, 2, and then zeros everywhere else for my diagonal matrix, but your eigenvalues down the diagonal, right? For your matrix P, that's a D. It looks like a P, doesn't it? That's a D, okay? Since I wrote my -3 first, I want to write the eigenvector that's associated with -3 first, okay? I'm going to multiply everything by 3 just so I get rid of the fractions. So I'll use -1, -2, 3 there. Since we wrote -1 second, I'll multiply everything by 6, use -2, -3, 6 for that one. Or you can leave, if you want to leave the fractions, it's fine. I'm just clearing them. Okay. And in the next one, we would have -1, -1, 2. So there are those fractions. This is my matrix P that I will use. That's my matrix D that I'll use. How you got the D? Remember, we had -3, -1, -2 are our eigenvalues. That's always going to be our eigenvalues. The order doesn't matter as long as you're consistent. So what I mean by that is, if I put -1 here and -3 here, then you would flip the 2 columns here. Okay. You just have to match them, right? So if I scroll back up real quick, so my lambda here will be your, whatever, the lambda1, lambda2 this way, lambda n this way, right? So notice that I'm matching the P1 and the lambda1. That's the associated eigenvector that we need. Okay. I can flip-flop my order as long as I flip-flop both orders. that make sense? This one okay? What questions do you have on this one? We're doing another one. This all right? Okay. All right. So let's do the next one. We could notice this one might be a little bit easier to do by hand since we've got that 0, 0 in there, right? We can expand along that row. Okay. So let's see if we can make sure we remember how to do our determinants here by hand. So again, subtracting the lambda off. The lambda I off, I mean, just has the effect of subtracting lambda down the diagonal. I see those 2 zeros down in row 2, or row 3, I mean. So I'll expand along the third row. And this will be a positive because anything on the main diagonal is positive. So I don't have to worry about changing that to a negative sign. So it'll be 3 minus lambda times that. And now that we have a 2 by 2, I can just multiply down the diagonal and then multiply the off diagonal and subtract. So we get 6 minus lambda times negative 1 minus lambda and then minus a minus 12. That's where the plus 12 comes from. Again, we want to figure out where this is equal to 0, so I want it factored, so I don't want to multiply this 3 minus lambda through it all. But I do need to multiply this piece out here and refactor. Okay. So we've got lambda squared, what is that? Minus 5 lambda, minus 6 plus 12. Here we've got, this will be lambda squared minus 5 lambda plus 6. That factors as lambda minus 2 times lambda minus 3. This is the opposite of lambda minus 3. So this really factors as lambda minus 2 times lambda minus 3 squared. Notice in this case we get a repeated root. Okay? This is when you have to be careful. This is when it's possible for a matrix not to be diagonalizable. Okay? Still might be diagonalizable if we can find that diagonal matrix in the invertible matrix P. That's what we mean by diagonalizable. Okay? We have to be careful when we don't. If we have distinct eigenvalues all the time, if we have n distinct eigenvalues, then it's always diagonalizable. That's not a problem. Okay? It's when we get these repeated roots when we might have issues. Okay? All right. So this tells us that we've got that our eigenvalues then, this determinant is equal to 0 when lambda is 2 and lambda is 3. Are we okay with that process? Is that okay? Just algebra, right? Literally algebra at that point. Okay. All right. What do we want to do with these eigenvalues now? Once we find the eigenvalues, we want to find what pairs of eigenvalues? Yeah, the eigenspace, right? We want to find those bases for the eigenspaces, right? We want to find the eigenvectors. So what do we want to do with the 2 and the 3? Yeah, plug them in and row reduce, right? Plug those in for lambda and row reduce the corresponding matrix. So if I flip back over to our calculator again, let me just enter the matrix B. Oops. Let me clear that out. Edit the matrix B. It's a 3 by 3, 6, 2, negative 1, negative 6, negative 1, 2, 0, 0, 3, Sure, I typed everything in right. Not C. There we go. So I just went and grabbed the command again. I want to row reduce B minus the 3 by 3 identity times a 2, because one of our eigenvalues is a 2. And I'll just do both at the same time so I can write them down here. The other eigenvalue is 3. And so there's our row reduction for that one. So for lambda equal to 2, the reduced row echelon form is 1, 1/2, 0, 0, 0, 1, 0, 0, 0. For lambda equal to 3, we got 1, 1/3, 1 2/3, negative 1/3, and then the rest are zeros. All right, so let me flip back over. Whoops, flip back over. All right. How many free variables do we have in the first matrix? 1, right? What was the power on the factor for lambda equal to 2? 1. So it has multiplicity 1, right? So notice in that case, we've got multiplicity 1 for the root, and we've got dimension 1 here for our eigenspace. We've got 1 free variable, so that's dimension 1. Over here, how many free variables do we have for lambda equal to 3? 2. Power on the lambda minus 3 factor. 2. Multiplicity 2 for the root, dimension 2 for the eigenspace, because we have 2 free variables. That's what we want, by the way. We want the multiplicity of the root to match the dimension of the eigenspace. That'll get us diagonalizable. We're going to summarize that on the next page. Okay. All right. So let's write down our basis for our eigenspaces. This one, which variable is free? Yeah, the x2 is free, right? The x2 is the free variable, right? What does x3 have to equal? So look at my x3. What does it have to equal? 0, right? That says x3 equals 0. There's a pivot in that column, right? Then our x1 is going to be negative a half of x2, correct? All right, for the other eigenspace, we have 2 basis vectors. We have a free variable in x2, and we have a free variable in x3. So one of our basis vectors will have a 1 where the x2 component is and a 0 where the x3 component is, and vice versa for the other one, right? If x2 is 1 and x3 is 0, x1 has to be negative 2/3. And if x2 is 0 and x3 is 1, x1 has to be positive 1/3. Okay. Okay. All right. All right, so what do you think we want to use now for our diagonal matrix? What goes down the diagonal again? Eigenvalues, right? So what do you think we want to use? Yeah, 2, 3, 3. Yeah. So we're going to repeat the eigenvalues since we've got 2 factors of the lambda equals 3, right? The multiplicity as a root, the multiplicity is 2. So I'm going to use it twice. And then zeros everywhere else. Tell me an eigenvector associated with 2. Yeah, the negative 1/2, 1, 0, or you could use negative 1, 2, 0 if you wanted to multiply it by 2 and clear the fraction. For the other ones, we're going to use each of these basis vectors. So, and again, here, the order doesn't matter as long as I'm consistent. Both of these are associated with 3, so I can use it either order and it'll work. It doesn't matter. Okay, so we can have -2, 3, or -2/3, 1, 0, and 1/3, 0, 1. You could also write it in the other order and it'll work. The good news about these problems is that you can check them. If I multiply P times D times P inverse, I have to get back to the matrix I started with. It's the whole point of this, right? Once I create this, we can check our answer. Okay, so let's do that real quick, just so that we can see it. So matrix, I'll do it as a C here. No, I don't know why I keep doing that. 3 by 3. Let's make my I'm going to make that the P matrix. So I'm going to make this -1/2, -2/3, 1/3, 1, 1, 0, 0, 0, 1. And I'll make my D the diagonal matrix. That was 2, 0, 0, 0, 3, 0, 0, 0, 3. So I just use D for the diagonal since we think of D and being diagonal. Okay. So I want to do the C matrix times the D matrix times the C matrix inverse. And I should get the matrix that we started with, which we do. Because I can check if I just pull up the B matrix, it's the same thing. Again, these are the fact that you can actually check your answer, make sure you actually get what you're supposed to get, is a nice feature of these problems, right? Again, the whole goal is to write the matrix in that fashion. Just to illustrate real quick that the order doesn't matter of those last 2 columns. I can change this one to 1/3 and -2/3 and 0 and oops, that should have been a 1. This would be a 0, this would be a 1, and then this would be a 1, and that be a 0. So I can flip those columns around, the second 2 columns around. Both of them are associated with lambda = 3, right? So it shouldn't matter the order. I should get the same answer. Okay? If I go out of that and just recalculate the thing we did, I get the same matrix again. As long as you put wherever you have the eigenvalue for that column, if you have an associated eigenvector in the same column of your P matrix, it'll work. Okay? So the order doesn't matter as long as you're consistent from one matrix to the next. Does that make sense? So for example, your diagonal matrix could have been 3, 2, 3. You just need to make sure your first column is an eigenvector associated with 3, second with 2, third with 3, and it'll still work. Literally does not matter. Any questions on the process at all? Are we okay with the process? Finding eigenvalues, finding eigenvectors, placing them into matrices? Is this okay? Okay. All right. So let's finish this off then. I talked about, pardon me, I talked about roots and having multiplicities, and I talked about eigenspaces and having dimensions of your eigenspaces. So that's these 2 definitions. We have algebraic multiplicity of an eigenvalue and geometric multiplicity of an eigenvalue. Algebraic multiplicity is the multiplicity of the eigenvalue as a root of the characteristic polynomial. Okay. In the previous example, we had the characteristic equation was that, right? In that previous example. Okay. We said the power on here was a 1, an understood 1, right? The power here is 2. So for lambda equals 2, the algebraic multiplicity is 1. For lambda equal 3, the algebraic multiplicity is 2. That's what we mean by as a root of the polynomial, that's what its multiplicity is. It's that power on the factor that you see. Okay. For geometric multiplicity, that's the dimension of the eigenspace associated with the eigenvalue. So in the previous example, we had one vector in the basis for our eigenspace for lambda equal to 2. So the geometric multiplicity was 2, or excuse me, was 1 for lambda equal to 2. We had 2 vectors in our basis for the eigenspace for 3. So the geometric multiplicity was 3 in that previous example. Or is counting basis vectors, or you like to think about it a different way. When you do your row reduction, it's going to be the number of free variables that you see, right? Number of pivotless columns. Okay. So just to write that down for your previous example. The geometric multiplicity of lambda equal to 2 is 1. And the geometric multiplicity of lambda equal to 3 is 2. We're not going to prove this, but it turns out that your algebraic multiplicity is always at least as big as your geometric multiplicity. However, it is possible where the geometric multiplicity is smaller. And that's when you're going to get a matrix that's not diagonalizable. Okay? So, just to write that down, for a matrix to be diagonalizable, that's a lot of syllables. It's almost a syllable per letter there. All right. For a matrix to be diagonalizable, we need the algebraic multiplicity to equal the geometric multiplicity for every eigenvalue of the matrix. If they're not all equal, we cannot get n linearly independent eigenvectors. Okay? The multiplicities have to be equal. The algebraic multiplicities all have to equal the geometric multiplicities all the way through in order to get n linearly independent eigenvectors. Now again, if you've got distinct eigenvalues, eigenvectors associated with distinct eigenvalues are always linearly independent. So if all your algebraic multiplicities are 1, all your geometric multiplicities will be 1, and you're good to go. It's when you get repeated roots where you might have an issue. Now the previous example, no issue, right? Previous example, we were good. Okay? So let's look at this example. I bet it's not as good. Just guessing. Right? All right, so let's do this one. Let me go over here. I'll call it C just because it says C in the problem. I said I'd call it C and then immediately tried to edit A. All right, so our matrix C here is 7, -4, 0, 1, 3, 0, -2, 5, 5. I'll go back into our Y equals menu. I typed the matrix into C, so I'm going to change my A to C here. But I'm going to graph and get my eigenvalues, just like we did before. I just need to change my A to C. There it comes. That looks weird. What kind of graph does this remind you of? Yeah, it was like a cube, right? Right? Notice that this is an odd multiplicity. We crossed the x-axis there, but it flattened. So this has to have multiplicity 3. That root has to have multiplicity 3 in this case. Okay? So it crosses at 5, it looks like. So I'm just going to flip over just real fast. So we see that our determinant of A minus lambda I, if I go through and actually calculate it, it should be negative of lambda minus 5 cubed. I know it's negative because, remember, we subtract the lambda off the diagonal. And so we would have a negative lambda times a negative lambda times a negative lambda to give us the cube. Why not that factor out the negative there? Doesn't matter for the multiplicity, but just to illustrate what that is. So what's your eigenvalue then? What's the only eigenvalue we have? 5. Good. So our eigenvalue is lambda equal to 5. Its algebraic multiplicity is what? 3. Yep, it's the power on the factor that gives you the 5, right? Its algebraic multiplicity is 3. That's the only eigenvalue we have. Remember, when we count the multiplicities, all the algebraic multiplicities is going to have to equal whatever the dimension is for our matrix. Okay? The characteristic equation can only have 3 roots, counting all the multiplicities. So we've counted all 3 roots already. The roots are 5, 5, and 5. All right. Let's go back over to our calculator. Let's do our reduced row echelon form here of C minus the identity matrix times 5. This, again, will do 2 things for us. One, it will verify that we really do have that as an eigenvalue, right? When we row reduce, we should see a row of zeros, at least one row of zeros. That'll verify for us that we really do have an eigenvalue. Okay? That makes sense? Okay. All right, so in this case, we do this. The second thing it'll also help us find the eigenspace. We got 1, 1, 0. There's our reduced row echelon form. So, all right, so for lambda equal to 5, we plug that in. Our reduced row echelon form is 1, 0, 0, 0, 1, 0, 0, 0, 0. How many free variables do you see? 1. Well, the very last column, right? What are the other 2 components going to equal? 0. So what's the geometric multiplicity in this case? How many basis vectors do we have with that eigenvalue? Just 1. Yeah, so its geometric multiplicity is 1. Is this matrix then diagonalizable? No. Algebraic multiplicity is 3 for that eigenvalue. Its geometric multiplicity is simply 1. So it's not diagonalizable. Since the algebraic multiplicity is not equal to the geometric multiplicity for that eigenvalue, we see that C is not diagonalizable. Was it 7 syllables? It's a lot of syllables. Just violates my law of conservation of syllables. It's too many syllables for that word. All right. Again, process for finding diagonal matrix and the invertible matrix, this diagonalization process. Is that okay? I'm okay with that? Any questions on that at all? Always equals the number of free variables. That's correct. Yep. What I'm handing out now are just topics from the old stuff that we've done. Yeah, well, I have new stuff. For what you might want to look at for the final. I think I posted them. If I haven't posted them, I will post review problems for the new stuff. So 4 linear transformations and 4 eigenvalues. But for the old stuff, it's stuff that we've used all semester. So it shouldn't be really necessarily review. It's stuff that you've already done. So talking about systems of linear equations. Well, we've done all sorts of things that involve systems of linear equations, right? All sorts of things. This is solving systems of linear equations, finding bases for eigenspaces, right? Homogeneous versus non-homogeneous systems. Okay, well, we're solving a homogeneous system here to be able to find eigenvalues and eigenvectors. Being able to, do our basic operations with matrices, that's pretty standard, right? You should be able to add, subtract, multiply, quote unquote divide. It's not really a divide thing, right? Dividing really means multiply by the inverse. Finding inverses, doing transposes. Your reduced row echelon form, of course, we use that all the time, right? Identify pivots, identify free variables, tells us lots of different things. Okay. None of those will be standalone questions. Okay, that's stuff that you have to know how to do to answer other questions, right? So I don't need to have standalone questions for those things. You have to know that stuff. All right, determinants. Well, besides knowing those different properties that I have listed there, we have to, if I ask you to find eigenvalues by hand, you have to know how to take a determinant, right? We've done that in a couple of cases, okay? So again, probably not going to be a standalone question about finding a determinant, right? Probably going to be, I'm going to ask you to find eigenvalues and ask you to do it by hand so that you need to know to take a determinant. All right, what else do I have on there? So linear transformation stuff, that was the stuff that we finished up right before we were doing eigenvalues and eigenvectors. Being able to find the matrix of a transformation, in particular, finding a standard matrix with respect to standard bases, but also, you got a non-standard basis, being able to find those and being able to work with them, right? One of the things I noticed on the homework that I handed back, when you have matrices for transformations that are non-standard bases, you've got to make sure that you're using coordinates for your input that are respect to that non-standard basis. So one of the problems that I asked you to figure out a transformation of a polynomial in 2 different ways. A lot of people were putting in just the coordinates for the polynomial with respect to the standard basis, but that's not how the matrix of the transformation was created. You got to find those coordinates with respect to the non-standard basis and then do your matrix multiplication. All right. Being able to figure out kernel and range. Again, kernel is everything that gets mapped to 0. Range is the same thing as your column space of the matrix of the transformation. So you should be able to identify both of those from the matrix, row reduce it, that kind of thing. 1-to-1 and onto, should be able to tell that from the matrix. But you also should be able to tell me some things about whether or not a transformation can be 1-to-1 or onto based on the sizes of your domain and codomain, right? So if the dimension of your codomain is bigger, it can't be 1-to-1. If the dimension of your I said domain, I think, but I'll say it again. Dimension of your domain is bigger, can't be 1-to-1. Dimension of your codomain is bigger, can't be onto, right? Those kind of relationships. Being able to do inverses of transformations, again, using the matrix of the transformation. And then being able to do compositions, again, using the matrices of the transformation. Those ideas. For vector space stuff, I mean, well, a lot of it's knowing what the words mean and being able to use those words in the new stuff that we've done. So a couple of things from the old things that I will expect you to do. You don't need to memorize all of the axioms. Remember, there were 10 of them. Okay. However, if I give you a setup, then you should be able to verify if an axiom is true or not. Right? I'll tell you what the axiom is I want you to verify. Okay. I might also ask you, if I give you a setup, what's the 0 vector for that particular space? That was a problem I asked on a previous test, right? Okay. So fundamental concept there. Might do a short proof with vector spaces, like showing the 0 vector is unique, or 0 times any vector gives you the 0 vector, or anything times the 0 vector gives you the 0 vector. We've done those short little proofs that we've done before. Being able to verify something as a subspace, right? That one's not so bad because you only have to show 2 things if something's a subspace, right? Closure under addition, closure under scalar multiplication. Linear independence and span. Well, we've talked about those ideas in lots of contexts. We just talked about needing linearly independent vectors to be able to form that invertible matrix, right? The diagonalization stuff, right? Span goes along with onto, right? You think about spanning the entire range of things, okay? So notice that those concepts pop up in linear transformation stuff as well. We just talked about basis and dimension of finding bases for eigenspaces, talked about dimension of eigenspaces, right? So again, words that you need to know to do the new stuff that we've done all along. Coordinate vectors, you need to know how to find coordinate vectors to be able to form your matrices for transformations, right? And being able to do computations with the matrices for transformations. Row space, column space, null space, that stuff pops up in transformations as well. And in finding eigenvalues, especially null space. All right, and then we had inner product spaces. Again, we had those inner product axioms. Not necessarily worried about memorizing the axioms, but being able to verify something if I give you a non-standard dot product, a non-standard inner product. Making sure you know all those definitions of how is length defined, how is distance defined, how is angle defined in terms of inner product, and being able to use those definitions with a non-standard inner product. Okay? Not something horribly onerous, just making sure that you understand that not every dot product is just the sum of the product of the coordinates. Okay? And you had ones like that on the test over the inner product stuff too. Okay? Finally, eigenvalues and eigenvectors, that's the stuff that we just did. Not anything tricky, not any proof kinds of things. Know how to find your characteristic equation, know how to find your characteristic polynomial idea. making sure that you remember that we talked about if we had, say, a matrix at an eigenvalue and we square it, we get the square of the eigenvalue. If you cube it, you cube the eigenvalue, and then the eigenvectors don't change, right? Same thing works for inverses. You should be able to think about those types of properties. Finding bases for eigenspaces, doing the diagonalizable stuff. And then finally, I believe we had 27 equivalent conditions to a matrix being invertible. I'm sure something about mega theorem will pop up. If we've kept track of it all semester, then probably something's going to pop up in the final about it. All right. I'll be around both Monday and Tuesday. I have a final at 10 on Monday, so I won't be in the office from 10 to 12. But rest of the day until I have a faculty meeting at 3:30 on Monday, I'll be around. Tuesday, I should be around all day. I don't think I have anything going on Tuesday. Not that I remember off the top of my head. Our final scheduled for 8 on Wednesday. Again, if you don't want to take it at 8, but you want to take it earlier, just let me know. We can schedule a different time for you to take it. Okay. All right. We're all done. Woo-hoo. Have a good weekend, everybody.